it couldn't get that a red square could move to the right.
Right. Yep.
So it changed the square into a circle midway through.
Yes. Yep.
And this was part of their proof that it was an out of distribution error
Yeah.
because it had only memorized, and this is a key word, right? It had only seen and therefore memorized certain shapes and certain colors going certain directions.
Yep.
So even though this is a two-dimensional example, it's a profound one, and you can see how it'd be easy to miss this, right? In terms of out of distribution. Welcome to Practical AI, everybody. My name is Jeff. I'm with Peter Lynn. This is our second season of Practical AI, and we are sponsored by Pocket AI. Pocket AI is a tool used to debug your models. With Pocket AI, you can prune your models to get 60%, or you can prune over 60% of the weights of your model without decreasing accuracy at all. Pretty cool. Peter, another bombshell coming out of MIT, and if I was going to give it a sort of a layman's summary, it's that AI isn't as smart as we think it is. Maybe it's not smart at all, and maybe we are a lot farther away from this thing called super intelligence than we thought. So I'll periodically play this video, but tell us a little bit about what they discovered.
This is a paper out of MIT where so this is a technique called sparse autoencoders, which Anthropic has also written about earlier this year. So the idea is you feed the language model a prompt, you see what parts of the network fire, you take that and you feed it through a sparse autoencoder to figure out like, hey, interpret this and tell me what's happening. So that's the basic idea. And from that research, this group realized that like actually we can identify parts of the model and group them like a human brain, like different lobes, where like here's where the speech is, here's where the chat is, here's where that is. And so they did some experiments where they did a very specific training. They did a circle and square. The circle was one color, the square was another color. And then they asked it to do other things. And what they found was that anything that you prompted that was out of the distribution of the data, it just failed basically, which means that it's actually not generalizing. Because the definition of generalizing and generalization in ML is it's able to do things on data that it hasn't seen, or it can do things accurately on the kinds of data that's never seen before.
Yeah, and out of distribution is a phrase that's used quite a bit in AI, and essentially what it means, from my perspective, is that the test data makes up the distribution, and when you try to see if something is if the AI is good at either generating or recognizing something that wasn't in the test data set, that would be out of distribution. And what you're saying is that the models are having a really hard time with anything out of distribution.
Exactly.
Now, in the world of video, which we're kind of focusing on here today, this MIT's discovery was essentially looking at the video models, Sora and whatnot, and they were discovering stuff out of distribution because they were seeing weird errors. But
Yeah.
maybe until they kind of did a little bit of research, they didn't realize that the video, the generated videos were failing. And so tell us a little bit about how they discovered that, and I'll play kind of some of the stuff that they were doing.
Yeah, so there's a video where they prompted to do a glass, and the glass suddenly bounced up and then broke, which was not what the prompt asked it to do. And so they wanted to investigate like why did that happen? Right. So yeah, so it's this cup animation. And so the question was, does Sora understand the laws of physics? Well, based on this prompt, it doesn't, because it's doing things that doesn't follow the laws of physics. Yep. And to investigate, what they did was they did this experiment with red squares and blue squares and red circles and blue squares, where they trained it and then they tried to prompt it to generate a new video. And what they found was it basically failed.
Yeah, this was interesting, Peter, and that was they basically exposed that there was a hierarchy of
Yes.
things, which I thought was interesting. It could be another topic, but shape, colors, whatnot. But when they said if something moves to the right or left and it's red, or depending on how it was trained, um, it couldn't get that a red square could move to the right.
Yep.
So it changed the square into a circle midway through.
Yes. Yep.
And this was part of their proof that it was an out of distribution error
Yeah.
because it had only memorized, and this is a key word, right? It had only seen and therefore memorized certain shapes and certain colors going certain directions.
Yep.
So even though this is a two-dimensional example, it's a profound one, and you can see how it'd be easy to miss this, right? In terms of out of distribution.
Yep. And this ties back into the previous paper from Apple claiming that really large language models are just doing sophisticated pattern matching, that it's not actually reasoning. And this supports that because if it reasoned, it would understand the laws of physics, but it clearly doesn't, because why would a cup suddenly float up and come down and break?
Yeah.
Like that makes
Well, and they had in this video, and we'll put this in the discussion, but it had a pretty good basic example of what this would look like, and that is if you showed it maps,
yeah,
and it was maps of each state, but you left out a state, and then you traveled to that state,
yeah,
it couldn't, because it hadn't seen it, it couldn't generalize like how to function with a map because
right,
it hadn't seen it, that particular map.
yeah,
And it's a good example of how it's not generalizing,
yep,
right? Because a human would do that no problem.
yeah,
Yeah, it would just say, okay, I've seen maps before and I'll just go over here. But this one was really struggling with it. So it's not reasoning like we had hoped. Now, just real quick, and I don't want to get too deep into this because it is complicated, but um, there are other people working with other methods to
yes.
get there. So give us a sort of the other tech and just a real quick sort of Cliff's notes on transformers again, because that's predominantly what people are using for AI.
Right. So transformers basically is this idea that if you have a memory, which this is the paper, memory is all you need, or attention is all you need. So using attention, they're able to train these large models, billions of parameters or trillion parameters, that figures out how language works and figures out the patterns in language. And so that's all great for producing a model that's humongous that can see patterns and recognize patterns. But where it fails is this: if it's stuff it's never seen, it fails. So there's other approaches like Yang LeCun and Meta have the JEPA approach, JEPA. People can Google that. There's the spiky neurons from MIT. So there are other methods that people are exploring that isn't just transformers. Because transformers is basically one, how do you train it? Well, we can remove words, ask it to predict it, and it learns the structure of grammar and the structure of like sentences and paragraphs. And it does that by using what's called the attention of memory, where it has key values and it remembers the relationship between tokens. And so everything is about tokens and then relationship between tokens. But that's not how humans work. Humans have a concept of like a chair. Like a chair could be anything. It could be an office chair, it could be a stool, it could be a rock, it could be anything. But to a language model, it doesn't really know because it has no concept of a chair.
Would you say the JEP something?
JEPA. Yep.
Yeah, I think the other word, correct me if I'm wrong, object driven, if you're doing research, is that that's another way to look up that?
Yeah, so there's variations on object-driven approaches and JEPA and DJEPA, which is the video version. They're different approaches for basically taking the training data, having it learn the actual abstract concepts. And then the abstract concept is what underlies kind of how it operates. Whereas LLMs, transformers, are really just based on the current evidence, it's just a fancy pattern matching system.
And therefore a long ways away from general
Yeah.
intelligence.
Right. So like OpenAI AGI thinks like, well, yeah, sure. If you go up to maybe 10 trillion parameters, you'll cover 98% of the things that people want to do. But how much is it going to cost you to train a 10 trillion parameter model?
Okay, so I mean that, and we'll wrap up here shortly. But what I'm hearing you say is that at least the OpenAI people, they may understand this problem, but they still think they can get there with transformers. Is that still the?
I think they believe that they don't have to get to the model that Jan LeCun is going for. That if they just scale up transformers and throw money, electricity, and power at it, look at something that works basically good enough to call AGI without it actually being able to handle out of distribution.
Okay. Here, good topic, another fun one. Be fun to keep an eye a little bit on the advancement of these other techs relative to transformers, because that would be obviously a significant shift, especially if they can do stuff with less power, less training data, right?
Yep.
All that is the big moats right now that are out there in AI. Good. Please like, subscribe, and ask us questions. We'll try to be here for more good content, and we will see you next time. Thank you.